Alrighty, reviewing the short answer questions of the practice exam. Number 1, an unknown metal is found to have a density of 7.8748 grams per centimeter cubed. So you got a density of 7.8748 grams over centimeter cubed. And it's crystallized in a body-centered cubic lattice. So body-centered. Well, I know that a body-centered cubic lattice has 2 atoms. The edge length of my cube, so if this is my cube, the length is equal to 0.28664 nanometers. Oops, didn't want that. Calculate the atomic mass. So we want atomic mass, so grams over mole. All right, so I have no indication of anything getting me moles, but I know that I can use Avogadro's number to get anything that I want, any unit per mole. So I'm going to have to use that at some point. Another thing that I notice is that I need mass. Now, looking at this, where can you get mass from? The density, great. So I can get mass from my density. So I have to get rid of my volume. So first, I have to find volume. So volume of a cube is equal to the length times width times height, or length cubed. 2 things that I notice. I'm given my length, but in my density, it's in centimeters. My length is given in nanometers. So that means that I have to make sure that I convert to the proper units. So you can first convert and then find the volume, or do it all at once, doesn't really matter. Another thing that I want to point out is it was told to you 2 atoms per unit cell. This may or may not be given to you, and it's something that you have to remember for the exam. So volume is equal to 0.28664 nanometers. Now these are the prefix conversions I have to remember. I remember that I have 10 to the negative 9 meters in 1 nanometer, and that I have 100 centimeters in a meter. That's how I remember it. And then I have to cube the whole thing. And when I plug that into my calculator, convert, and then cube to get the volume, I get 2.36 times 10 to the negative 23rd centimeters cubed. All right, now I can use that to get my mass. So I take my 2.36 times 10 to the negative 23 centimeter cubed, multiply by the density. Then you can see centimeters cubes cancel out, and you get 1.858 times 10 to the negative 22nd grams. Now you still want per mole. So that means you need to know how much mass is in this unit cell. So in this unit cell is 2 atoms. So how many grams this is for 2 atoms, because this whole cube takes up 2 atoms. So to get per mole, we have the 2 atoms to give us the appropriate quantity. So then you take your mass, and that's the mass of the entire thing, but we know the cell itself only occupies 2 atoms, and to get the appropriate atomic mass, we need to take into account our 2 atoms, so you would divide by the 2 atoms, and then convert to per mole using Avogadro's number. Your atoms cancel out, and your answer would become 55.96 grams over mole. Now, you can always double check, because if you ended up getting 0.67 or 0.55, something kind of went wrong, because we know atomic masses usually range from the 1 all the way to 200s. Okay, moving on. So if you start with a piece of ice at negative 21.7 degrees Celsius, and you put it in a calorimeter that contains 91.3 grams of water at 23.4 degrees Celsius, then the entire mixture reaches 11.8 degrees Celsius at thermal equilibrium. Determine the mass of ice that was added to the water. So it says here to sketch a Keating curve. Again, that hint is probably not going to be given to you on the actual exam, but I would think it helps. So that's why I put it here. So think of it like this. You have this ice cube, right? And this ice cube is at negative 21.7 degrees Celsius. and it's added to this cup of water where we have the mass to be 91.3 grams, and that water is at 23.4. So I know that when I put something cold and something warm, it's going to melt and there's going to be a change of heat going on. However, ice doesn't just melt. The melting point of ice is 0, so I know first I have to reach 0 degrees Celsius, which means that my first heat is the ice warms to melting point. Then, once you reach the melting point, there's no more temperature change because the phase change happens at this temperature. So then, my ice actually melts. Well, then the water that was formed begins to warm up more. So then my third heat that's happening is the ice water warms to thermal equilibrium, the 11.8 degrees Celsius. So the ice first has to reach the melting point, then it melts, then it warms up because it even hasn't warmed up to thermal equilibrium. There's more heat transfer going on. Now we can't forget about the other situation. We have the water originally too. Now this is releasing heat, right? Because the water goes from 23.4 to 11.8. So once that ice melts, and the ice water begins to warm up, the original water in the solution cools down. So you have your ice warming to the melting point, the ice that melts at its melting point, the ice water that reaches the thermal equilibrium, which will then all be the absorption as the original water releases the heat to reach the thermal equilibrium. The water cools down. So then you think, okay, when I have warming, I have to endure a temperature change because I have to reach the melting point. So this would be MC delta T of my ice. Then my second heat, I melt. There's no temperature change. So that's when I look at the heat of fusion since I'm melting. So I look at the mass times the heat of fusion. Then once I melted, I warm up to my thermal equilibrium. So again, MC delta T, where this time you are water, and at first you start with ice. Then your heat released is equal to also your mass times your specific heat times the temperature change. Now that you have your process, you would just plug your numbers in, knowing that you don't know the mass. So, whoopsies. I would leave my mass as M and then multiply it by my specific heat of ice, 2.01 joules per gram degrees Celsius, times my temperature change. Now, I'm going from negative 21.7 to 0. So that means I have 0 minus negative 21.7. And that's added to the mass, which I don't know, times the heat of fusion, which is 333 joules per gram, plus my ice water, which is still the mass that I don't know because I don't know what the ice was. So again, M times my specific heat of water, which is 4.18 joules per gram degrees Celsius, times my temperature change. So I reached 11.8 from 0, so 11.8 minus 0 degrees Celsius. And that is all equal to my water cooling, which becomes my mass of water, which I know, 91.3 grams, times my specific heat of water, 4.18 joules per gram degrees Celsius, times my temperature change. Well, my temperature change is 11.8 minus 23.4 degrees Celsius. So then you finish all of your little calculations and leaving M if you want to use X because you don't know the mass, since you're solving for the mass here of the ice. So I get 43.61 M plus 333 M plus 49.324 M is equal to, the negatives cancel, 4,426.95. You isolate and you get that the mass of the ice is equal to 10.4 because I want 3 sig figs grams. So it's thinking about all the little processes that are happening as something is melting or cooling. Again, it doesn't just happen in one process. There's all these little things of reaching at the melting point, having a phase change, the temperature that's involved, that makes these simple processes of when you put ice into your coffee, it cooling it down, and the ice melting, and you drinking it. Alrighty, answer the following questions based off of the diagram below. So we have a phase diagram. We know the phase diagram is solid, liquid, and gas. So let's label this first. Well, I know that anything at 1 atmosphere with a temperature is my melting or boiling point. So 1 atmosphere to 113.6 is my melting point. So that means that this is my solid and this is my liquid. And this would be my fusion curve because it's in between the solid and the liquid. Then I have 184.4 with 1 atmosphere, so this is my boiling point, which makes this my gas and this my sublimation curve. Therefore, this is my vaporization curve, kind of just to label it, because a normal boiling point and a normal melting point always occurs when the vapor pressure is equal to the external pressure, which is 1 atmosphere. So when you're looking at the plot and you're trying to figure out where everything is located, look at where the temperature is at 1 atmosphere. So when you see that, you can then realize kind of which lines indicate the solid, liquid, gases, and in between are the phase change curves. So what is the normal boiling point for iodide? So we just figured that out. That's 184.4 degrees Celsius. What is the melting point for iodide at 1 atmosphere? 113.6 degrees Celsius. What state is present at room temp and normal atmospheric pressure? So room temp is around 25 to 30 degrees Celsius. So that's all the way down here somewhere. That means we'll be at solid. What is the state present at 186 and 1 atmosphere? So 186 is somewhere around here, and 1 atmosphere is over here. So you could be anywhere between the solid and the liquid and the gas. So I'm going to say liquid and gas phases are both possible. Alrighty. What is the number of carbon atoms in a diamond with a volume of 0.0454 nanometers cubed and the density is 3.52 grams per centimeter cubed? Okay, so I want atoms. So I already know if I want atoms, molecules, ions per mole, I'm going to need to use my Avogadro's number. I'm going to say that this gives me atoms per mole. So I'm going to have to use molar mass somewhere. That kind of tells me. Which I know of carbon is 12.01 grams per mole. Because I need atoms, and to get atoms, I have to get rid of moles. So then I need grams. Okay, well, I'm given my density, so I can get my grams from my density. Again here, I'm given the volume. So I can use my volume and density to get my mass. But note that the unit is not the same, so you first have to convert. So I take my 0.0454 nanometers cubed and convert to centimeters. Now, how you do this conversion is totally up to you, but just make sure that you are converting and cubing everything. So there's 10 to the 9th meters in 1 nanometer, but since the nanometer is cubed, we have to cube that. And same with the fact that there's 100 centimeters in a meter. You cube that, and you get 4.54 times 10 to the negative 23 centimeters cubed. Now I can use that to find my grams, multiplying by the density. Centimeters cancel out. You're left with 1.598 grams yet, times 10 to the negative 22nd grams, and this is of carbon atoms, since we're talking about the density and the volume of the carbon atoms in a diamond. Okay, so now where would you go from here? So let's think about this. You want to end up with atoms. Right now you just have grams. You're not told what kind of a cubic cell you have where you can divide by the number of atoms. Just like, because in the other problem, you were told body-centered cubic unit cell. Okay, when it's a body-centered cubic unit cell, I know that for every unit cell, there's 2 atoms. So that mass, I would divide by 2 atoms to get the appropriate amount. But here, you're not given that information. But you still just want to know how many atoms this whole diamond occupies. How can you go about that with little units and factors that you know? Well, you know that you have to end up somewhere using Avogadro's number. And you know it has to be the last step because you want the atoms. That's the unit you desire. So you have to find the in-between step. Well, what I notice is I can use molar mass to go to moles. So then I say 1.598 times 10 to the negative 22nd grams per carbon times 1 mole carbon over 12.01 grams times now my Avogadro's number. We'll get rid of my grams, my moles, and I'm left with 8.0 atoms. And that's it. So it's just, again, it's all these different things of just dimensional analysis that we work throughout the entire semester, picking it apart, thinking about what you have, knowing that even when you're not given molar mass, you're not given Avogadro's number, you always know that. That's always handy for you. And like, what units does that represent? To pick it apart, sometimes just going backwards. Alrighty, moving on. When 250 milliliters of methane gas is burned at 25 degrees Celsius and 744 millimeter mercury, what is the mass of ice that melted when 15.5% of heat produced escaped? So 15.5 produced of heat that was made was gone. So what is 100 minus 15.5? 84.5. So that means 84.5% of heat actually helped this process because 15.5 escaped. So I notice here I have my volume of methane, .250 liters. I have my pressure of methane, I have my temperature of methane, and that's it. Well, I'm going to probably need to use these units because I have everything that I visualize is ideal gas law. But how does that work here? I'm also given my heat of fusion for the solid and the liquid of water. Okay, let me go back. Let me read this again. When 250 milliliters of methane is burned and the ice melted, well, I know methane burns in oxygen to make ice. So you know what? I'm just going to write my combustion reaction. Let's just do that. So methane plus oxygen makes carbon dioxide and water. Now note here, when your methane is burned, makes carbon dioxide and water, if it ain't sealed, your carbon dioxide is gone because you can't keep the water. But your liquid, you can't keep the carbon dioxide, but your liquid is still there. So now if I reread this, it says all this amount of methane was burned, and it's asking for what is the mass of the ice that melted when 15.5% of heat produced. So basically, what happened was that methane produced heat, and that heat helped melt ice. So you have to kind of work backwards here. I want the mass of ice melted. Okay, well, I know I can get mass from molar mass. I can get the moles from the kilojoules per mole. So I have to isolate the kilojoules. And to do that, I need to know the amount of heat from my combustion of methane. Well, I'm not given my heat of combustion. But what I can do is I can calculate my overall heat of reaction because I always know the heat of formations of my products minus the heat of formations of my reactants. So if you were to look at the back of your cover sheet, I'm just going to scroll down really fast, and your heats of formation are given, that's where they would be located, and you would calculate. So you have your carbon dioxide, which we have 1 of. I'm missing a 2 here. So then you would have 1, so negative 393.5 plus 2 times negative 285.5. Now this is heat of carbon dioxide, heat of water, minus methane, negative 74.8, plus 2 times 0 for plus, excuse me, I said bless you to myself. Anyways, okay, so 2 times 0 cancels out, and then you calculate that the heat of the reaction is equal to negative 890.3 kilojoules per mole, or just kilojoules, right? That's the unit. But we can say, because when we write a reaction, we can say the heat of the reaction here is equal to negative 890.3 kilojoules, which obtains to every part of the stoichiometric coefficient of the reaction. So what it means is that the heat that was released by the methane combustion gave water enough to melt. So heat of the water is equal to the heat of methane. Well, I know that methane is negative 890.3 kilojoules. Now the stoichiometry is 1, so per 1 mole of methane, that looks like a negative sign. But I want to get rid of that 1 mole of methane because I just want kilojoules. So then I can use my heat of fusion. How can I get moles of methane? Well, I'm given all my ideal gas law factors, so I can use ideal gas to find my moles. So you plug everything in, making sure you convert to the appropriate units. And you get moles are 0.010 moles of methane. So again, this is what's happening. Methane got combusted, it got burned under these conditions. So you know the volume, the temperature, and the pressure that methane was burned, and you can solve the moles of methane that was burned. Well, through the heat of reaction equation, we can always calculate the heat released from the combustion of a reaction using the formations. So doing that, we found that the combustion of methane releases negative 890.3 kilojoules. That represents every component of the reaction. So it's negative 890.3 kilojoules per 1 mole of methane, or negative 890.3 kilojoules per 2 moles of oxygen, because that's the coefficient, etc. So what happens is that water was formed from the melting of an ice because of the heat that was made. So we already know that we're looking at 84.5 because 15.5 was escaped. So then we need to figure out the heat that was actually produced in the reaction to then melt the water into ice. So you had your combustion reaction, water formed, and then it formed into an ice, and you're trying to work backwards. Well, we know that we can find the mass from the moles of the water using the heat of fusion. So we have to isolate for that heat. So we solved for the moles, we solved for the heat of methane combustion. So now if I multiply this by my moles, I can find just my heat. But I'm not done yet because it's not 100% of that heat. It was only 84.5%. So then I multiply this by 0.845 to account for just the amount of heat that actually formed my water. And that comes out to be, the negatives cancel out because there's a negative already, 7.52 kilojoules. So that's the amount of heat that actually made the water. All right, so then I need to take into account how much of the energy is needed to melt, which is 1 mole over 6.01 kilojoules. Then I can use my molar mass to find my grams. And I get 22.6 grams of ice. So just, again, thinking really, really carefully about all the different processes that are happening. All right, an unknown gas sample has a density of 0.670 grams per liter at 755 and 209 millimeter mercury and 298 Kelvin. The sample of helium and argon gas, the sample is made up of helium and argon. What composition by volume exists in this mixture? Okay, so this is going to be something that's, whenever you have unknown, that's what pops out to me, and that I have helium and argon. I'm going to say that my whole sample, X plus Y, helium is my X, argon is going to be my Y, is equal to my overall density of 0.670 grams per liter. Okay, well, if I have a whole mixture and I know that it's made up of two things, what I'm going to do is I'm going to assume 1 liter of my entire solution since they were both a mix. So then what I can do is I can use my pressure and volume and density to actually solve for my moles of gas. Because I want composition by volume, I need to isolate for the volume of each. I can do that using the density and the molar mass. So I have to isolate first for how many moles are in my total solution. Well, I know that I have my pressure converting to atmosphere times 1 liter. Now again, I'm assuming 1 liter of solution because I know that it's a mixture, just like when we assume 100 grams of the sample or 1 mole fraction. 1 atmospheric pressure, we say 1 liter of solution since it's a mixture of multiple components. And that's divided by my R constant times my temperature. And then I get that my moles is 0.04063 moles total. So what that means is that my moles of helium plus my moles of argon is equal to 0.04063. Well, I can isolate my density equation in terms of X and say that Y is equal to 0.670 minus X. I know that to get the moles equal to each other, I have to divide by molar mass of helium and molar mass of argon. So then I can plug in my X over my molar mass plus my 0.670 for my Y minus X over the molar mass of argon equal to the total moles. You can do your algebra and you find that X is equal to, now again, all the moles cancels except grams, so X is equal to 0.10605 grams of helium, which you can then plug back into your equation and find that Y is equal to 0.564 grams of argon. So now that you have your masses, can you find your composition by volume? Well, you can use Pivner again to then find volume. So if you convert your argon or helium to moles, so 1 mole divided by 39.95 grams is equal to 22.5 moles. Then V is equal to nRT over P, and will be 22.5 moles times 0.08206 times 298 divided by, since they're all under the same conditions, 755 over 760, I get 0.347 liters. So if I subtract that from 100, I get 0.65. So I have 34.7% argon by volume and 65.3% helium by volume. Just setting up 2 equations and 2 unknowns for what you were looking for here again. Knowing that you can find the mass using the mole ratio, finding the total moles, and then you know the densities, again, isolating for a variable to make the same variable, solving for one to then help you solve for the other. Okay, just 3 more questions. Almost done. Methane combusts readily to form liquid water and carbon dioxide. Liquid water vaporizes at its boiling point. of 100 degrees Celsius, what volume of methane is required to vaporize water? 1 liter at 298 Kelvin in 1 atmosphere. Okay, so first sentence, methane combusts readily to form liquid water and carbon dioxide. I'm going to write my equation. I think that's really helpful. Okay, so then it says the liquid water vaporizes at 100 degrees Celsius. So basically, this combusted, and then water that formed went further and vaporized. We want to know what volume of methane was required to vaporize 1 liter of water at 298 Kelvin and 1 atmosphere. So this entire solution is under these conditions. What made that happen? Okay, so we already know the heat of combustion from that we solved earlier for methane was 890.4 kilojoules per mole. I know that in order for water to become a gas, that heat of vaporization is equal to 40.7 times 10 to the third joules per mole. I also know that that just doesn't happen because note how the combustion was at 298 Kelvin. That's not 100 degrees Celsius. That's 25 degrees Celsius. So the combustion was at 25 degrees Celsius. So the liquid water that forms first has to warm up. So water warms from 25 degrees Celsius to 100 degrees Celsius. And then water vaporizes to gas at the boiling point. So you have your first heat, which will be, since it's warming up to 100, mc delta T, and then your second heat, which will be your moles times your heat of vaporization. Okay, so my first step will be to calculate the amount of water that was needed to reach the heat of the boiling point. Now, I'm given 1 liter of water. For mc delta T, I either need the mass or I need the moles because I can also get the heat capacity of moles. So on the key, the heat capacity for water in moles is 75.2 joules per mole. Now, they're the same thing as saying the heat capacity is 4.18 joules per gram degrees Celsius. It's just per mole Kelvin instead of gram degrees Celsius. So since I have 1 liter of water, I know that that is 1,000 milliliters. And I know the density of water is 1 gram per milliliter. And then the molar mass is 1 mole over 18.01 grams, which then gives me 55.5 moles. So now I can find my Q. Now you can leave it in grams, you can leave it in moles. I'm just showing you the mole way since we usually do grams. So then Q is equal to the moles, 55.5 moles, times 75.2 joules per mole Kelvin, times the temperature difference. So 100 to 25 degrees Celsius, since I'm in Kelvin, that's 373 minus 298 Kelvin. And that equals 313020 joules. Now my second will be the vaporization. So the Q is equal to the mass times the heat of vaporization, or moles. So the mass is 1,000 grams times 40.7 times 10 to the third joules per mole. I just realized I can't use that. I have to use my moles, which is 55.5 moles times 40.7 joules per mole, and that equals 22,58850 joules. So then my total heat from when the water produced from methane combustion to boil will be the sum of my two processes, which is equal to 2571870 joules, which if you divide by 1,000 gives you 2,571.9 kilojoules. Okay, I'm going to draw a little line here. So I now figured out the amount of water that was vaporized heat-wise. I know my combustion, so if I then use the amount of heat from the reaction that was used to vaporize the water, I can use my mole ratio from my heat of combustion to find the moles of methane. This gives me 2.89 moles of methane. Again, because you have the heat of the combustion. Now, we needed to know after that combustion heat how much more heat was used to make that water. We're working backwards. So now that we've figured that heat out, we can use the overall heat of the reaction to isolate for the moles of methane. And then it just becomes the fact that you know ideal gas law to solve for your volume. The moles of methane that you solved for, the constant of R, the temperature 298 because that's what the combustion was under, divided by 1 atmosphere. When you plug everything in, you get that the volume is 70.7 liters. So it's knowing, you always know the heat of the total reaction. Now, just figuring out from there, if you know how much heat was taken afterwards to vaporize or melt or etc., you can always isolate for the moles of a substance if that's what you're looking for, mass, volume, etc. Okay. Liquid ethanol boils at 78.4 degrees Celsius under conditions of 15 degrees Celsius. What is the vapor pressure? Alrighty, so I'm given here ethanol. I have my temperature of 78.4 degrees Celsius. I have my second temperature, 15 degrees Celsius, and I want vapor pressure at 15 degrees Celsius. Well, if my boiling is at 78.4, I know that my vapor pressure is at 1 atmosphere because any normal boiling point or boiling point of a substance occurs at 1 atmosphere. So if I have 2 pressures and 2 temperatures, and I want the pressure of something, and I'm thinking of boiling and heat change, this is not pressure and temperature. You have to think of boiling. So that means you need heat of vaporization. Because this isn't just that the temperature was affected by pressure. This is vapor pressure, so it's not gas laws. So the heat of vaporization for ethanol is 35.56 kilojoules per mole. This is the Clausius-Clapeyron equation. So the natural log of the vapor pressure fraction over the heat of the vaporization over R is equal to 1 times T2 minus 1 T1. So then you would plug everything in. You want to convert your kilojoules to joules. Use your R constant for joules. Convert your temperatures to Kelvin. You find that your fraction of the pressures is equal to negative 2.9590. Then you take your natural log. You know that your pressure is 1 atmosphere. To get rid of the natural log, you take the E of both sides. And you find that the pressure is equal to 0.0519 atmosphere, which makes sense that it lowered since the temperature lowered, and they're directly related. So if you hadn't gotten a higher temperature, you know there would have been a mistake, because as the pressure lowers, the temperature lowers. All right, last question. Hydrocarbon can readily react to lower the pressure in a gaseous mixture. When a sample of ethine that is originally held at 7.8 kPa reacts with hexane, the total pressure reduces to 3.9 kPa. What fraction of ethine has undergone the reaction? There's no change in temperature and volume that occurred, so you can just look at pressure. So I have this reaction. ethyne going to hexane. Now I want to balance. That puts me at a 3 here. Now something you'll see at the beginning and throughout Chem 121 is making an ICE table. That means I for initial. Sometimes you'll see a triangle or C for change. So that's the change that happens in the reaction. So I is for initial. What is everything at? Your reactants, your products, what are they initially? C or the triangle is for change. So what change occurs during your reaction? And then E or sometimes F means equilibrium or final. So then what are you left at equilibrium or a final when the reaction has gone to completion? So I like to do that and start this as we go towards the last end of our semester in Chem 120 to get the idea of how to make these to visualize what's happening. So initially, what do you have for ethyne, C2H2? What do you know? Well, since everything is held constant temperature volume, I know that I have 7.8 kPa for my initial value. Now, my reactant is 7.8. My product hasn't formed yet. So initially, I have 0 product, right? Because this is before your reaction happens. Now, what happens as your reaction goes forward? What's the change? This is going to go away, right? This leaves as your product forms. So we say that's minus, right? Because that's going to go down and your product's going to increase. But you have to use the coefficient. So we say minus and then 3x. So 3 moles of the ethyne are going to go away as the 1 mole plus x of the hexane is going to be produced. And then you basically just put together what you created. So that means 7.8 minus 3x is what I would have in the final. So what I started with minus the 3 times the change and my product produced. So I know that my total pressure is equal to the partial pressure of both my substances. Well, I know that my total pressure is equal to 3.9. And I know that my pressure of my final reaction for ethyne is 7.8 minus 3x. And for hexane is just x. So now what I can do is isolate for x. I get 3.9 is equal to 7.8 minus 2x, because this is just plus 1, which then gives me that x is 1.9. So I said x was equal to the amount of hexane that formed. So I just figured out that the pressure of hexane is 1.9 kPa. Now, 7.8 minus 3x is equal to the amount of pressure of ethyne. So 7.8 minus 3 times 1.9 gives me that the pressure of my ethyne is equal to 2.1 kPa. So now I figured out the partial pressures of my reaction to give me my total pressure. But what I want to know is the fraction that underwent my reaction. Well, to get the fraction, that's my mole fraction. Now, how do my partial pressures, mole fraction and total pressure, relate together? Well, I know that the partial pressure of a substance is equal to its mole fraction times the total pressure. Now, do we have everything we need to actually solve this? Yep, you have your partial pressure, you solve for it, you have your total pressure. So you know that the mole fraction, the fraction that underwent the reaction, is equal to the partial pressure over the total pressure, which is 2.1 over 3.9, which equals to 0.53, that the fraction of ethyne underwent the reaction. So again, we've done this before so many times, just knowing this part, right? And you could have said, well, I say this is X and this is Y, right? And then solving for one and the other. Now, what I introduced here is making that table, because when you make this table, you see, okay, at the end of my reaction, I have to have something like this. Then you have the same variable undergoing, initially, this is what I started with. The change, now again, as you undergo a reaction, What are your reactants doing? Are they going to go away or are they going to be made? Your reactants are reacting. So they are reacting and they decrease. And as they decrease, your products form. So a change, now this could be any variable, it's usually just X, is always going to be minus X for reactants plus X for products. But you include your coefficient because that's how the mole-to-mole ratio of this balanced equation works. And then your final or your equilibrium is just the sum of the initial and the change. Now, because we did that, we were able to relate that to the total pressure to isolate for the pressures that occurred at the end of the reaction, to then apply it to the laws to find the fraction of molecules that were actually made. Now that's going over the entire practice test. Now again, I want to mention and stress that this is just a form to see the format, the types of questions. Now the questions on the test are going to be different. It's not going to be at all the same multiple choice or short answer. It's going to be the same material, but the questions could be more challenging, more longer, more shorter. Good way is to practice in this time frame. Look at different questions of this type of material to really practice for the test. My biggest advice is just picking apart the different questions that you see. That's the whole goal. So even if questions are different, we've done all of these things many, many times.